Like any star, it will run out of fuel in its core and it starts changing. It starts bloating and getting so large that it will engulf the orbit of Mercury and Venus and come very close to Earth. So imagine looking on the horizon and sunrise is half the sky. Over the past few weeks, the James Webb Space Telescope has recorded several shocking discoveries, but this one just about takes the cake. This discovery has revealed information that might negatively affect our planet Earth. Recently, a team of astronomers devoted time to studying the final frontier with the help of the James Webb Telescope. They had pointed it toward Betelgeuse, one of the most luminous stars that grace the night sky. The James Webb Telescope picked up an odd signal, which scientists interpreted immediately. This did not bode well, as the signal, after interpretation, revealed the possibility of a massive supernova explosion. What does this mean for us on Earth, and how bad will the effects be from this once-in-a-lifetime supernova event? Join us in this video as we explore how the James Webb Telescope just made a terrifying announcement about Betelgeuse's explosion. Betelgeuse is a star of such epic proportions that it is classed as a supernova. A regular supernova has to be at least 8 times more massive than our Sun. With Betelgeuse's immense size and power, irregular pulsations, and high unpredictability, the Betelgeuse supernova is a wonder that has left scientists in awe. Its extremities defy any attempt at explanation. In this recent research, scientists were frantic to see what the JWST alongside the Laser Interferometer Gravitational Wave Observatory would catch in space. They were, however, surprised when they retrieved the data that detected a light wave coming from the Orion constellation, where the Betelgeuse star resides. Betelgeuse is located at the left shoulder of Orion and is categorized as a semi-regular variable star. This means that Betelgeuse gets dim occasionally, but not regularly. The semi-regularity of the Betelgeuse star makes us understand that its distance from Earth is about 475 to 642 light-years away. It is also about 1,400 times larger than our Sun and 14 times brighter. The Betelgeuse supernova dims once every 430 days and every 6 years. Whenever each dimming cycle takes place, dark spots can be seen on the surface of the semi-regular variable star. In the same way, dark spots sometimes appear on our Sun's surface, only that it is larger. In February 2021, the supergiant experienced its dimmest cycle in a long while. The V-band magnitude, also called the dim cycle, had a magnitude of plus 1.614, which is still bright by all accounts, but is dimmer than the average light range. Betelgeuse's immense brightness is not the only thing the supergiant is renowned for. The star gets its signature reddish hue from its cool surface temperature, which sits at about 3,500 Kelvin, much cooler than our Sun, which has a surface temperature of about 5,500 Kelvin. Betelgeuse's low surface temperature means it emits much less energy per unit of its surface area than the Sun. It is due to this low energy level that it appears much dimmer than it should be, despite being one of the biggest stars known to us. Maybe it is content to sit on the sidelines and allow other stars to shine. Betelgeuse has been one of the most prominent celestial bodies gracing our night skies for the longest time. The superstar was noticed when the Greek astronomer Ptolemy noted its color as more orange-tawny. However, this was back when you could not tell anything about a star save for its color and position in the night sky. Modern astronomy, along with innovation and sophistication of astronomical and space-observing instruments, has allowed scientists to measure with near-perfect accuracy the intricacies of these celestial bodies. By analyzing the light that Betelgeuse emits, astronomers have figured out its size, temperature range, and chemical composition. The Hubble Space Telescope has provided many detailed images of the surface of the red supergiant, revealing its unique patterns of gases and dust clouds. These observations have allowed scientists to create real-life models of the star's behavior, enabling them to predict its future evolution. ALMA, a top-notch observatory in Chile, provided some ultra-high-resolution images of Betelgeuse's surface, bringing to light much new information about the red supergiant's structure and behavioral patterns. One of the most fascinating discoveries made using ALMA's technology is the presence of a vast gas plume extending from the star's surface. This plume, believed to be caused by the star's pulsations, may help explain the star's unusual behavior and how it is constantly changing. Betelgeuse's pulsations are caused by a phenomenon known as convection. This convection process causes hot gases to rise and cooler gases to sink. This up and down movement or motion creates waves that travel through the atmosphere of Betelgeuse, causing it to expand and contract. Betelgeuse's surface is also covered in dark spots, otherwise known as star spots or magnetic spots. These star spots represent areas where the magnetic field is strongest on the star. These dark areas are cooler than the surrounding gas as these magnetic fields inhibit hot gas flow from the star's interior to its surface. Betelgeuse's magnetic field is thought to be stronger than the Sun's magnetic field by at least several thousand. These strong magnetic fields trap gases in loops, resulting in regions of intense magnetic activities that are visible as these dark spots on the images we see. Star spots are not a feature unique to Betelgeuse alone. Many stars, our Sun inclusive, have these star spots. The dark spots on Betelgeuse's surface are thought to be many times larger than Earth's and cover up to 20% of the star's surface. The presence of star spots directly affects the brightness of a star, causing it to vary over time. This means the more star spots present on a star, the dimmer the star will be. This happens because the areas where the dark spots cover are much cooler, emitting less light than areas with weaker magnetic fields. This brings us to why astronomers are bothered by the recent gravitational wave readings from the Betelgeuse star. The dimming we discussed earlier has astronomers in a fix, as this is common behavior with stars reaching the tail end of their lives. The issue now is that stars of Betelgeuse's proportions do not wither away and die quietly. On the contrary, supergiants go off in a way worthy of their size, brilliance, and magnificence. Supergiants go off in a bang, a phenomenon known as a supernova explosion. Scientists have started to ponder the probability of Betelgeuse exploding at all, and if it will. They hope it will take place soon. One would imagine such an occasion would be crucial in studies regarding the cosmos. If it all goes according to the wishes of our researchers and the Betelgeuse dies off in an exploding ball of flaming gases, the effects of the supernova would be evident from Earth, even in the brightness of day. It is confirmed from the signs and data that Betelgeuse is giving that it is only a matter of time before the red supergiant bows out of the cosmos. However, the exact time this would occur is yet to be determined. From data gathered with the James Webb Space Telescope and the Hubble Space Telescope, scientists have figured out that just a couple of years ago, the red semi-regular variable star blew its top and lost a good chunk of its visible surface. As a result of this explosion, Betelgeuse is producing a large surface mass ejection that makes us wonder if it is finally about to explode in its entirety. This massive ejection in substantial dust clouds is a new experience for scientists. It is not a behavior typical of young or dying stars. Granted, even our Sun loses some of its outer atmospheres in some minor ejections referred to as coronal mass ejections, but it is nothing compared to the intensity of the ejection emitted by the Betelgeuse star. The mass ejected from Betelgeuse was about 400 million times more than the average coronal mass ejection. The JWST has revealed that the red giant is slowly recovering from the massive ejection. Although the star is still under observation by scientists, they remain puzzled by these recent occurrences. This recent phenomenon with the Betelgeuse star has provided a learning curve for scientists. The observations provided by the JWST have given some insight into how red stars lose mass when they're about to die. Scientists have discovered that they lose mass, or little bits of themselves, because their nuclear fusion furnaces burn out before blowing up in supernovae. The amount of mass lost always has a significant effect on their fate. The recent loss of a massive chunk of its mass by the Betelgeuse star is most likely the beginning of the assurance that the loss of the giant red star is at hand. Scientists and astronomers are particularly concerned about it and are devoting their time to seeking a much more definite answer to these questions. The massive ejection of mass matter by the Betelgeuse star is assumed to have been spurred by a convective plume over 1 million miles across, which bubbled up from deep inside the star. This plume bubble produced heavy pulses and shocks that caused a chunk of the star's photosphere to get blown away, leaving the star with a wide, cool surface area. Underneath the dust raised from the mass ejection, Betelgeuse struggles to recover from this massive injury. The mass it lost, weighing several times more than our moon, the liberated piece of photosphere zoomed off into space, where it cooled and formed a dust cloud that blocked the star's light from reaching the Earth. Apparently, this blockage caused the dimming of the star in 2019, which lasted several months. The dimming of Betelgeuse was so obvious that even amateur astronomers who did not have access to sophisticated instruments took notice of the intense drop in the star's brilliance. For at least 200 years, scientists and astronomers have studied Betelgeuse's rhythm and motions. These noticeable disruptions attest to the significant effects of the blowout of the star's photosphere. TRES, as well as the Hubble spectra, implied that the outer layer may return to normal soon, but the surface itself is still quite shaky as it waits for the photosphere to finish rebuilding itself. Our Sun has had its periods of coronal mass ejections as stated before, but the difference in magnitude between the Sun's ejections and the surface mass ejections that the Betelgeuse star recently experienced has made it obvious that the two events cannot be put in the same category. Betelgeuse has expanded so much over the millennia that if it took the position our Sun currently occupies in the cosmos, its outer orbit would extend past Jupiter's orbit. Betelgeuse's red hue indicates that the star has reached the stage that stellar bodies go through when they burn out their hydrogen reserves through their core, resulting in the eventual collapse of their core and its outer layers puffing out. Our Sun is still a reasonably young star and has far to go before reaching this stage. Scientists have deduced that reaching this maturity stage would take the Sun at least another 5 billion years. It has also been deduced that when the Sun swells into its mature size, its radius would increase into proportions reaching Mars's orbit. After the great dimming of the Betelgeuse star in late 2019, scientists took a special interest in the new behavioral pattern of the old star. Although the supergiant star regained its brilliance after a few months, scientists were curious as to the cause of the dimming in the first place. Many thoughts were brought forward, one of which suggested that it was a result of the star contracting before the explosion that would signal the demise of the red giant. However, the data obtained from NASA's James Webb Space Telescope, having revealed that the reason for the apparent dimming of the star was nothing more than the dust clouds raised from the ejection, shut down that theory. With the puzzle solved, scientists once more believe that the supernova would not occur for another 1.5 million years. It has been confirmed that Betelgeuse's color has changed from a yellowish-orange to red within the last 2 millennia. This piece of information, together with the theoretical calculation of the star being about 14 times larger than our Sun, with the mass being the defining parameter of the star's evolution, can be deduced that Betelgeuse is about 14 million years old. It can also be deduced that the red supergiant is in its late evolutionary stage, and in the next 1.5 million years, it would explode and die. Some scientists believe that merely detecting gravitational waves from the old red star is not enough to sentence the star to death. According to Salvo Vitellaier, a professor of physics at the Massachusetts Institute of Technology, the wave coming from the direction of Betelgeuse does not mean the wave came from Betelgeuse itself. Salvo further reminds us that just before a supernova, neutrinos are released. This has also not occurred. In addition, the fact that Betelgeuse still shines at night, even though it is relatively dimmer than usual, would not make Betelgeuse a likely candidate for gravitational wave emission. There is a possibility that what was detected was not even a gravitational wave. The wave intercepted does not have any of the known mergers. If this is true, then what would have caused the detected wave is a mystery. Noise from the terror activities on Earth may be a cause, but this possibility has been ruled out. Supernovas can be incredibly beautiful. They can take up several shapes and colors, but this depends on the type of supernova and its environment. Despite their visual appeal, we must remember they are as dangerous as they are aesthetically pleasing. One of these supernovas' main dangers is that they release high-energy radiation upon explosion. These huge bursts of gamma rays can be thousands of times more powerful than the energy emitted by our Sun. If these radiations hit the Earth, it can be deadly to life on Earth, as these gamma rays can damage the DNA of terrestrial life forms. Researchers are divided as to whether the Betelgeuse is about to go supernova on us. Some believe its time is almost done, while others believe the red giant still has a couple of tens of thousands of years in it. The last time a supernova appeared within our Milky Way galaxy was in 1604, or at the very least, the last one known to have been seen. It's possible that there have been further nearby supernovas since then, although they were probably hidden by atmospheric gas and dust. The Crab Nebula, whose light first reached Earth in 1054, is one of the remnants of supernovas that occurred in the past. The supernova seen in 1987 in the Large Magellanic Cloud, a tiny partner galaxy of the Milky Way, and given the 1987A designation, was the next best thing to Kepler's supernova in recent years. Other galaxies have also had a large number of supernova explosions, which are visible via telescopes but would have gone completely unnoticed by observers in Kepler's time. To put it another way, it has been a while since we last witnessed a star explosion in our galaxy. Our bright close supernova, therefore, do. According to astronomers, our galaxy should see between 1 and 3 star explosions on average every century. Therefore, a 4-center difference is a little larger than one might anticipate. The astronomers of today are considerably more ready for the next supernova than Kepler or anyone else would have been a few decades ago. The telescopes used by modern scientists can record visible light. These tools will demonstrate what a supernova would appear like if we were able to fly nearby and observe it directly. However, we also have telescopes that can capture infrared light, which has hues that are outside of the visible spectrum and beyond the red end. Since infrared light has longer wavelengths than visible light, it can penetrate gas and dust more easily than visible light, revealing objects that may be beyond the capabilities of conventional telescopes. For instance, the James Webb Space Telescope mostly captures infrared light. Although visible and infrared light are both a component of the electromagnetic spectrum, supernovas also generate neutrinos, which are subatomic particles. Detectors are now available to capture these neutrinos as well. Additionally, scientists now have detectors that can capture gravitational waves, which are thought to be released by exploding stars but are actually minor vibrations in the fabric of space-time. Supernovas come in 2 different varieties according to scientists. A white dwarf star sucks material from a partner star in a Type 1 supernova until a runaway nuclear reaction occurs, shattering the white dwarf and sending debris hurtling into space. A Type 2 supernova, also known as a core collapse supernova, occurs when a star that has run out of nuclear fuel collapses under the force of gravity. The collapse then bounces, causing an explosion. Depending on its nature, a supernova may light so brightly that it briefly eclipses the entire galaxy. However, Type 2 supernovae are particularly intriguing because, in addition to light, they also emit a significant amount of neutrinos. In fact, the neutrino emission may begin a little before the explosion itself. Neutrino detectors would probably catch the signal hours or even days before the explosion itself became apparent. If the red giant star Betelgeuse went supernova, Betelgeuse's brightness has fluctuated recently, and some scientists believed it was about to explode. More recent research, however, indicates that the dimming was likely brought on by dust clouds or sunspot activity on the star's surface. However, it is anticipated that the massive star will explode soon. Astronomers will be notified automatically if galactic supernova neutrinos arrive on Earth by the Supernova Early Warning System, or SNEWS, a network of neutrino detectors. The network will use data from 7 different detectors located in 6 different countries plus Antarctica to determine the supernova's approximate direction in the sky so that optical instruments can take a closer look. Today, astronomers are ramping up SNEWS 2.0, which will serve the same function as its predecessor but with improved triangulation ability. Neutrino science was still in its infancy when 1987A exploded, but 3 active detectors nevertheless managed to record 20 neutrinos. Thousands, or maybe hundreds of thousands of neutrinos could be captured by the global network of detectors if a supernova occurs right now within our galaxy. If a collapsing star is heavy enough, it may generate a black hole, in which case the whole explosion fizzles out. This particular scenario could produce an exceptionally startling signal. The neutrino stream would abruptly cease. In that case, that would be incredibly interesting because you could actually see this sudden cutoff that would signify the formation of a black hole. The missing star may potentially be found by astronomers searching through lists of known stars. According to Skolberg, if you see a blank, a missing star, that could be the location of a newly formed black hole. The biggest stars are the celebs of the universe. They are extremely uncommon, enjoy opulent lives, and pass away in ferociously destructive supernova explosions. Even though these phenomena are amazing to see, they can take on a menacing tone when they happen closer to Earth because an explosion within a specific minimum safe distance would be extremely dangerous for people on Earth. We have discovered that roughly 3 million years ago, a star burst close to the Earth, on the Moon, as well as in ancient samples of deep ocean material, radioactive iron atoms, iron, 60, or 60 Fe have been discovered. These distinctive atoms are minute distinguishing pieces of supernova explosion waste. Thus, for the first time, we can study the nuclear flames that drive exploding stars and disclose explosions that occurred before recorded human history by using marine deposits and lunar cores as telescopes. Additionally, an explosion that happened so close to Earth was likely a near-Earth, which released a lot of radiation that may have been hazardous. Earth has faced several challenges during the course of its 4.5 billion-year existence. The globe has been in danger from numerous disasters such as enormous impacts, volcanic conflagrations, and cold episodes of snowball Earth. However, life goes on. Similar to fireworks on Earth, supernova explosions are spectacular to view from a distance, but can be hazardous to onlookers who are too close. There are two ways that all neighboring supernovae can harm the biospheres on worlds similar to Earth. Gamma rays with high energy are released throughout the first few weeks and months. This radiation would be prevented from reaching the ground by our atmosphere, but at a huge cost. The ozone layer would be severely harmed. High-energy cosmic rays arrive with the explosion blast wave to the solar system thousands of years after the event. In addition to harming the ozone layer, these also produce penetrating muon particles that directly irradiate terrestrial and marine life. Some supernovae release high and prolonged X-ray radiation for the first year to 10 years following the explosions, which can seriously damage the ozone layer. When a star is covered in a dense blanket of gas that was earlier released by the star itself in a strong wind, such explosions radiate the maximum energy. The kill distance to these events is much greater than it is for the other processes mentioned above because of how powerful the X-ray emission is. The whole result is to make these comparatively infrequent X-ray bright supernovae a threat on par with the other more ordinary explosions. In other words, the danger in the galaxy has increased. Supernovae are undesirable. They have the power to destroy biospheres and cover worlds with lethal radiation. The ozone layer of a planet can be destroyed by a particular kind of supernova years after the explosion, according to a recent study, which adds a new potential danger. The brightness from hundreds of billions of stars combined can be eclipsed by a single supernova. To put things in perspective, consider that Betelgeuse is about to explode. The star is more than 600 light-years away from us, but when it goes supernova, it will still be the second brightest object in our sky, behind the Sun. Betelgeuse, which shines brighter than a full moon, will be visible during the day. It will be so dazzling for a few weeks at the height of the explosion that shadows will be cast even in the dead of darkness. Despite its terrifying brilliance, a supernova's visible light emission only makes up a very small amount of its total energy production. Furthermore, while exposure to high levels of visible light may result in blindness, it generally doesn't have many other detrimental impacts. The high-energy radiation linked to the supernova, which typically takes the form of X-rays and gamma rays, is more concerning. High-energy radiation has the ability to catalyze oxygen, removing the ozone layer that shields the Earth. Without the ozone layer, life on Earth's surface would be subjected to the full force of the sun's UV radiation, which could result in an extinction event. Within the initial few seconds of a supernova, a radiation blast occurs, but a greater threat emerges afterward. Eventually, hundreds or millions of years later, cosmic rays, which are subatomic particles accelerated to almost the speed of light, erupt from the maelstrom. They can also shred ozone layers and cover planet surfaces with deadly radiation, in addition to carrying a sizable portion of the total supernova energy with them. Such occurrences might have occurred in the past. Significant levels of iron, 60, a radioactive isotope of iron created only in supernovas, are found in deep-sea cores and lunar regolith. According to analysis, iron, 60 is a sign that Earth was recently struck by a supernova ejecta, possibly within the last few million years. Astronomers have previously determined that we are pretty safe. There are no close supernova candidates that can endanger life on Earth based on the dangers posed by gamma rays and cosmic rays. However, astronomers have discovered a fresh possible threat. A specific type of supernova has the potential to emit deadly radiation that is additional long-range and dangerous to worlds like Earth. When a star nearing the end of its life is surrounded by a substantial disk of material, a specific class of supernova arises. A shock wave arises after the initial supernova explosion and strikes that disk. The shockwave causes the disk to become extremely hot, which in turn leads the disk to generate a lot of X-ray radiation. This radiation has a high energy density and a very long range of travel. The brightest X-ray supernovas can overwhelm a planet's ozone layer, depleting it by as much as 50%, which is more than enough to cause an extinction event out to an astonishing distance of 150 light-years, according to a recent study by astronomers. Such supernovas would deliver a lethal 1-2 blow. A fragile planet would be bombarded by X-rays months or years after the initial outburst. The cosmic rays would then arrive hundreds or thousands of years later and complete the task before the biosphere had time to recuperate and replace its protective covering. Could life on Earth be in danger from a close supernova? Theoretically, yes, but the explosion would need to be quite close. This is fortunate because a close supernova's radiation blast would be disastrous. The explosion would release gamma, X, and UV radiation over a few weeks. These rays wouldn't necessarily reach Earth, but they would destroy the ozone layer's protective layer. Nonetheless, although it wouldn't transform us into the Hulk, it would remove the stratosphere's ozone layer. Without the ozone layer, the planet would be inundated with the sun's lethal UV radiation, which may destroy oceanic phytoplankton and have a cascading impact on the food chain, possibly causing a mass extinction. It's possible that such a thing has happened at some point in the history of our planet. A global extinction that occurred at the end of the Devonian period some 360 million years ago may have been caused by a supernova, according to scientists. They point out that rocks from that time contain plant spores that appear sunburned, as though blast-tested by ultraviolet light. Recent evidence suggests that the ozone layer suffered a catastrophic global loss 359 million years ago, near the conclusion of the Devonian epoch. Thankfully, there aren't any supernova candidates nearby right now that could be dangerous. The extinction saw the demise of many land-dwelling tetrapods, but those who survived also happen to have 5 toes, as do their descendants, including humans. If the Devonian extinctions were triggered by supernovae, then we can literally count the ways these explosions have impacted us. Thankfully, no candidate X-ray supernova has been found to be close to Earth, but the galactic habitable zone, the area in each galaxy where life can exist, is now subject to additional restrictions as a result of this research. Star formation is insufficiently high in a galaxy's farthest regions to produce the elements needed to generate rocky planets. However, the dense centers of stars where stars live and die quickly are equally fatal because frequent supernovae irradiate the area around them. According to the new research, the galactic habitable zone's inner boundary is likely located further from the galaxy's core than previously thought. Earth is located in one of the galaxy's safest neighborhoods, despite occasionally being hit. Supernovae, however, also produce new things. Many of the heavy elements we rely on, such as the oxygen we breathe, calcium in our bones, and iron in our blood, were created in nuclear reactions that took place deep inside exploding stars and spread throughout space as a result of the blast waves they generated. According to astronomers and physicists, we are made of star stuff, to quote Carl Sagan. So, do we fear them or welcome them? Thanks for watching another episode of Voyager. While you're still here, make sure to click the video on your screen for our next episode.